webinar under the theme Railway Ballast Stabilization and Mitigation of Ballast Degradation using Geogrids. This event is brought to you by the Indonesian chapter of the International Geosynthetic Society, INAIGS. My name is Rifa Nurkayungyun, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this morning. First, I will be reading the rules of the webinar. Second, there will be opening remarks by a member of INAIGS, Bapak David Saputra. After that, the event will be guided by Bapak Michael Dobi as our moderator to start the presentation of our speaker, Errol Tutumluer, PhD. The event will then continue with a Q&A session. We would like to ask you to stay with us until the end of the event because we will be doing a quiz with a total of 250,000 rupiah for 2 winners. We'll also give you... Ladies and gentlemen, for your own convenience, please put attention to the following rules. You can submit your questions for the speaker through the Q&A feature located at the bottom of the screen. The question should be in English. You can raise your question before, during, and after the presentation of the speaker. We expect you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speaker. This event is also live streamed on the INAIGS YouTube channel, or you can directly go to the link bit.ly/live-INAIGS-Mar 2022. If you have any questions, please contact Sandy at the number shown on your screen or on the chat box. Now, without further ado, I would like to invite Saputra to give his opening remarks. To Bapak David, the time is yours.
Okay. All right. Good morning, ladies and gentlemen. Now, on behalf of the Indonesian chapter of the International Geosynthetic Society, or INAIGS, I welcome you all to our second geosynthetic webinar in 2022. This monthly webinar is one of INAIGS's programs to share valuable knowledge from distinguished speakers from Indonesia and abroad to our members and, of course, our participants from everywhere, absolutely for free. Now, today, I am delighted that we have invited an insightful speaker who will give a presentation titled Railway Ballast Stabilization and Mitigation of Ballast Degradation using Geogrids. The speaker today is Errol Tutumluer from the University of Illinois at Urbana-Champaign. Now, we welcome you, Errol, and thank you in advance for sharing your knowledge and insight in this event. I also would like to welcome you again, all participants. Thank you for your participation in this webinar. I hope this webinar series can be a good source of valuable knowledge of geosynthetics from geotechnical experts for you all. Now, I also thank all the committee members who has set up this webinar. Please enjoy the webinar. Stay safe, and thank you.
Okay, thank you, Bapak David, for your kind remarks. Ladies and gentlemen, now this webinar will be guided by our moderator, Bapak Michael Dobi. Before I give the floor to Bapak Michael Dobi, I would like to remind you that you can start submitting your questions from now, during, and after the presentation by using the Q&A feature. We would also like to remind you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speakers. Now, please welcome our moderator, Bapak Michael Dobi. To Bapak Michael Dobi, the time is yours.
Thank you very much, Rifa, for your very clear introduction. And I have a great honor today to introduce our speaker for this second webinar of 2022 organized by the Indonesian chapter of the IGS. Before I do that, I just also like to give my thanks to the organizers of these events. As I always like to mention, they do a lot of hard work behind the scenes to make these events successful. And of course, to the attendees, to everybody who logs in or tunes in or comes in on YouTube to listen to these events, thank you also for your time in attending, because these events are, of course, being created to help spread knowledge about geosynthetics, as mentioned by David just now. And I hope that you will get everything possible out of this. So today, our speaker is Errol Tutumluer. We just had a quick check on being able to pronounce his family name correctly, and I'm doing my best, but the important thing is we will refer to him as Errol, because this is a very nice name and how we would normally do it here. One thing to mention to you is that Errol has never yet been to Indonesia. So his first trip here is unfortunately a virtual trip. Maybe at some stage in the future we can actually welcome you properly, Errol, to this country, because it's a very, very interesting place to visit if you've never been here. You've already heard quite clearly about the topic of today's webinar. It's to do with railway ballast and essentially minimizing degradation of railway ballast by the use of geogrids. Obviously, you're going to hear a lot more about that when Errol starts to speak. And I think it's also worth mentioning that in all of our webinars so far, they have been mostly aimed at structures. So we now have another webinar, though, that is more aimed at what I'd call the horizontal or pavement type of application, rather than looking at walls and slopes, which we've mainly looked at in the past. So this is of great interest. I think you might remember also last year that Professor Jorge Zornberg also talked about this kind of application, but this was more to do with the construction of road pavements over expansive soils. So this is in that category of application of geosynthetics, which is a very important one. And I said you'll hear a lot more about it today. So Errol is professor at Department of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign. And I'd have to say, I've actually been there. In fact, with Sandra, my wife, we went there a few years ago. It's a very lovely campus. It's situated quite a long way south of Chicago, but a very nice big open campus. And it was a great pleasure to make a visit there. I'm so sadly I didn't meet Errol there on that visit, and that came later. But you will see from his CV and experience that Errol is very active in his field, and he's delivering a lot of lectures as well as carrying out a lot of extensive research into pavement materials, in particular granular pavement materials. Now, in contacting us over the last few days, Errol also sent us a link to a lecture he presented just last week at the ASCE Geo Congress, which was on pavement materials, and it was what is called the Carl Monismith lecture. And I listened to it. It's a very interesting lecture. And I think what you will see if you listen to that and also from today, is that Errol is trying to provide a much better and fundamental understanding of how granular materials work, if you like, and how we can model them better, if you like, to move away from purely simple empirical methods and move much more towards a more fundamental understanding. And the kind of work that Errol has been involved with is very much in that direction. If anybody would like to get the link from that lecture, we can certainly post it to you or let you have it. Now, amongst many of Errol's contributions to our engineering activities, he is an IGS council member, and in fact he's the chair of the publication committee, so directly involved in our IGS activities. He's also the chair of the ISSMGE TC202 committee on transportation geotechnics. Well, I think I must stop talking and allow Errol to deliver his webinar. But just to let you know, I met Errol at the 11th International Conference on Geosynthetics, which was in Seoul, where we actually we got together with two very well-known names of JP Giroux and Jihan to deliver a workshop on geosynthetics in pavements. And that's how I got to first meet and get to know Errol. And that was an incredible experience. And and I'm certainly looking forward to listening again to some of the information and work you've been carrying out, Errol, in this particular area. Railway ballast, yes, it's a very interesting area, and it's an area where geosynthetics have a great deal to offer. So I think that's all. I've taken up enough time, Errol, and I will hand over to you, and I'm looking very much forward to this lecture. And now the floor is yours, and please, everybody, attention now for railway ballast. Thank you, Errol.
Thank you, Mike, for this very nice introduction. Indeed, it's my pleasure to be here with you today. And thanks to David, and thanks to the Indonesian geosynthetic IGS organization, the IGS, I believe, for this nice invitation. Again, this is my first time virtually in Indonesia, but hopefully it won't be my last time, and hopefully in person I will come and visit. So with that, let me share my screen quickly with my presentation here. All right. Just to confirm, you're seeing my screen, correct?
Yes, Errol, clear. Yep, we see it.
Excellent. And now the slide view here, presentation view.
Correct. Also
excellent.
Perfect, yeah.
Thanks again. Thank you, Mike. And once again, it's my pleasure to be here actually in front of you today to talk about some of the work we've done on ballast stabilization and mitigation of ballast degradation using geogrids. I've been working on geogrids for almost 2 decades now, and some of that recently got applied, especially in the last decade, to railroad ballast stabilization, and that's what I will talk about mostly. But as Mike very nicely covered my background on unbound aggregates, which is primarily what I work on as a professor at the University of Illinois at Urbana-Champaign. So I'm directly affiliated and involved with actually activities of Illinois Center for Transportation, more on the payment side, both for highways as well as airport payments. And then we have another center called RailTech, also established at UOFI, or University of Illinois at Urbana-Champaign, and I'm involved with them working on the railroad side. So aggregates are building blocks in every kind of infrastructure, materials and layers that we construct, and of course unbound aggregate layers being one of them. So with that, this presentation again is very much on railroads, and let me start by saying a few words about railroads and some background on the railway track structure, which is where we will come in now with the geosynthetics need. Again, especially freight railways are very dominant in the United States, and rail is the principal means of economically moving large and heavy freight long distances over land. And U.S. has huge lands, and you can clearly see like a unit train here as a coal train. You can tell with the open rail cars actually, and the coal dust in the air, as you see hundreds of cars carrying coal, in this case, from the central United States to some of the plants, basically for burning coal and coal burning plants, right? This is one way that unit trains are often, as freight, as number one, rail is used. Rail is also used for other types of freight, such as intermodal containers, such as other things, and diesel locomotives are usually the most commonly used in the United States. But again, just to emphasize here that rail transportation combines the speed and energy efficiency in such a way that nowadays we talk about sustainable transportation efforts. 1 ton of freight can be transported 500 miles with just 1 gallon of fuel. This is hard to beat with any other transportation mode when you think about that. Of course, in addition to those advantages, I will talk about some other things now, how to build infrastructure related to this freight railroad, and freight railroad often jointly used by passenger lines, and I will get into that as well. Here's a map of North America that shows actually United States as well as Canada, and the heavy lines that are in different colors. The yellow color is about 15 to 50 million gross tons of freight carried. And then there's the green ones going up to 100 million gross tons, MGT they usually call it, right? And then you see over 100 million gross tons. This is exactly the coal. Powder River Basin and the coal transportation in Wyoming and other states, bringing the coal to some of the energy plants right here in the middle of basically the country. That's exactly where Illinois is, very close to where I live, as Mike mentioned. And this picture very nicely shows then those heavily used freight lines in North America, a total of about 140,000 miles of track network. When I looked at Indonesia, I found about 4,100 miles, roughly about 35 times probably U.S. has the trackage as for the rail network. And when I looked at the volume of transported freight in Indonesia, I found the numbers going up to 47 million metric tons or so. Between the U.S. short tons and I guess metric tons, the conversion is 1.1, metric ton being a little smaller than the U.S. short tons. But nevertheless, interestingly, the mileage is about 35 times, to the trackage is 35 times greater in the case of U.S. And when I compared here the typical tonnage, actually, or millions of freight tons per year, there's about 350 times difference in the way that we carry, I guess, a total of 18.6 billion short tons of freight in the U.S. So there's a heavy usage. Probably U.S. is second to, in terms of the heaviest. U.S. is second to Australia, I would say, but most often with Australia on the freight trains and how heavy they can get, they're kind of competing, right? And that's exactly what you see here. Often gross rail load is what's denoted here, is what we use. Again, this is in pounds, but I have some of the metric tons as well. Typically what happens is that what we call as heavy haul freight transportation lines, like those coal lines or so, we go to really heavier cars, and these are individual rail cars going up to 286 kips or 315 kips, and that really relates to 35.8 to 39 tons. This is what we call heavy axle usually. In metric tons, about axle loads going up to 32 to 35 metric tons. So this is quite heavy, right? But it's not just the end of the story, because a lot of these heavy freight that we carry on these lines, which are typically ballasted track, just like in Indonesia, we have also passenger trains using the same trackage. And especially now we're trying to get our passenger trains to go faster, nothing like dedicated lines to go very fast, over 300 kilometers per hour or so, like in China and Asia and many other places in Europe, right? We are maybe approaching something like 240 kilometers per hour in what we call as our heaviest traveled passenger line, the U.S. Northeast Corridor, all the way from Washington, D.C. to Boston, about 440 miles in between, typically, but heavily used by passenger trains again. We call it a higher speed, with the 240 being the maximum in kilometers. But the challenge is in the same trackage, right? How can we actually maintain the ballasted track? And this is often the ballasted track that you see with both the passenger trains and those heavy freight trains. Again, freight trains are very heavy. Passenger trains are much less heavy, or they're probably about half or less in terms of how their tonnages are, how their axle loads are, but in general, they're much faster, right? And there is the issue of safety concerns, especially when both are being used on the same trackage and the shared track and the shared right-of-way. So just like Indonesia, I mean, in the U.S., pretty much all of our lines, the trackage, over 90%, maybe 95% easily owned by freight rail companies, right? So from that perspective, often Amtrak trains or passenger trains have to share those lines with the actual freight lines. So how to get things working on a ballasted track, which consists of a track structure that's seen here, often we call the superstructure right here, sleepers or cross ties, we call them, or simply ties in the US, right? And the rails on top, as well as below the cross ties or sleepers, what you have is the ballast, the sub ballast, and then the prepared subgrade. So again, and when you think about the ballasted track, it's a bunch of aggregates, just rocks that are supposed to carry the load. Of course, they do other things. And if you just quickly visit what their functions are, when you look at a typical track structure and the substructure, especially we're interested for carrying the load that's transmitted down below the tie. Ties are often concrete ties and heavy lines, heavy axle load lines, right? But often you will find in the older lines or more commonly wood ties, they're actually distributing the load. Well, first of all, the ballast, the rocks are resisting the track forces. That is, they're providing a track bed basically for the combined cross ties or sleepers and rail, which are connected with the fastening system. So often the lateral stability, longitudinal stability, all of those are important to keep the trains traveling on that rail in the track, in that bed of ballast, so resisting track forces, providing resiliency, almost like a bed of the seabed, kind of, right? The ballast is supposed to take all the load and provide the tolerance and resiliency. With that, provide void storage, right? And often ballast starts to degrade, and we'll talk about that. That's how the bottom part is kind of filled, right? There's more voids maybe towards the upper part of the ballast. And but we can actually adjust things, and especially geometry corrections, that's how they facilitate, ballast facilitates maintenance. The biggest thing about ballast is that it's uniform size rocks, so it's supposed to actually take time to fill all these voids, and in between, that's what we call degradation or fouling often. It's supposed to provide proper drainage in addition to, of course, carrying the load and distributing the load and the stresses, and it's just to make sure that the subgrade actually is not getting those high wheel load stresses. What about the subballast right underneath? Subballast, in especially new lines, it's a very common practice, typically constructed a lot in the US. They're supposed to take also the load and reduce further the stress so that they protect the subgrade underneath, the prepared subgrade soil, that is, right? Sometimes it's called formation. It's supposed to provide a layer as subballast, almost like a pea gravel size in this case, as opposed to ballast is much larger, right? About 50 to 75 millimeter size particles. But subballast is supposed to provide kind of a layer in between, again, the subgrade soil and the ballast, and protecting from frost damage, providing frost protection, providing a separation layer between ballast and subgrade such that there's some filtration going on, right? So filtration meaning that some separation. Subgrade is not supposed to pump in a typical mud spot or typical spot that you will see the track getting wet. We should have the subballast prevent that kind of subgrade soil pumping into the ballast layer. It's supposed to also shed water away from subgrade and serve all these purposes as an intermediate layer. So it's supposed to also provide somewhat drainage, but hopefully you can do a better job with some geotextiles and geosynthetics used from that perspective as well. And that's also something effectively used as part of subballast. I'll talk more about, again, ballast stabilization, though, with the geogrids, especially using geogrids. I will get to that in a few minutes. So understanding the heavier loads, as the loads get heavier, what happens often when you look at the implication of trains getting heavier and heavier because you want to carry more with one pass and so many rail cars or so many cars being pulled by a locomotive, right? Often 20-30% increase in the load, you will say that, oh, that's not a problem. Slowly we're increasing and the typical tonnages and the weights of the gross rail loads of the cars and things. But actually, its implication, its effect on the subgrade from a settlement perspective is not that linear. Usually you double, triple, sometimes even for a 20-30% increase in the load level. So that's why it's very important for us, which actually tells us here that we need to understand how to design the thicknesses of ballast just to protect the subgrade, right? Because you don't want to overstress that. That's the primary cause of settlement and primary cause of some of the vertical deflections that you will see. So this granular layer thickness design came out with some really pioneering work from Professor Silic, a very well-known authority in this area in ballast and ballasted track. Professor Silic from University of Massachusetts and his students, now deceased, but his students are very active in the railway community. That's how they came up with the thickness of the ballast and sub-ballast should be anywhere from, for ballast, 9 to 15 inches. Again, 1 inch is about 2.5 centimeters, right? You can multiply, and then sub-ballast 3 to 6 inches. So I go switch between the units in my presentation, don't have a chance to adjust them all for metric. But that should give you an idea how thick we want. And I will talk more about that. What are some conditions we determine those thicknesses and how we come up with those thicknesses? Again, by understanding how failures may occur due to that weakest subgrade layer and how we need to limit the stress going on top of that subgrade to prevent progressive shear failure or excessive plastic deformation conditions. And I will show you what those are actually, those two especially, what a progressive shear failure often encountered is, especially with channelized traffic in the railroad case. And the second one is the excessive plastic deformation, again, directly under the wheels. So just to give you those two failure criteria here, here you see a typical ballasted track with the clay subgrade. Often what happens is with the extensive loading, repeated loading always coming from the rail down, you see that bearing capacity failure, the shearing effect, right? And that progressively causes more and more shearing like that, and some pockets opening up here, more ballast then moves into in that direction as the shearing takes place, and that's what's called progressive shear failure. Now, related to this, or could be related to directly consolidation and further deformation under wheel loading, the second criterion for failure also has a similar picture where you see those pockets that are opening up directly due to some of that shearing, right? Those pockets I call because, see, there is a depression zone. That's the typical surface of the subgrade, but that's because of the settlement and the partial shearing that took place, right? And often that's where the ballast is migrating and going down. And often these pockets hold water. They're also called water pockets, so to speak, because trapped water is there. So that's the mechanism of how failures in the track substructure, especially in the subgrade, takes place. And you end up losing a lot of ballast into those, and you keep replacing, bringing new ballast, but sometimes losing into those mud spots. How can we prevent some of that? There's one application of geosynthetics here in railroad subgrade stabilization. When I say subgrade stabilization, again, that soft subgrade, which has become even softer maybe in time because of the water pockets formed under the rails, and by placing a geosynthetic directly below that sub-ballast layer, you see now you actually provide a shear layer, a stiff layer, that's actually holding very well on top of the soft subgrade and doesn't allow that progressive shear to take place, and actually improving because it cuts the shear bearing capacity slip line, right, it improves the bearing capacity like that. So that's one way that geosynthetics, when placed under sub ballast, will improve basically load-taking ability, bearing capacity. Now, interestingly, when you think about what percent of most of track substructure maintenance or track structure maintenance is actually spent on really rebuilding the subgrade and the sub ballast and the ballast. When you think about all of those, right about 6 years ago, exactly this time, I attended the Railroad Research Review, and Colin Basie, the principal investigator working on this project, had this pie chart. I think this was very relevant because $2.4 billion in the U.S. spent, as noted by the research arm of the Association of American Railroads, TTCI here, Transportation Technology Center. They indicate that a majority of that goes into rail repair and maintenance, but then actually I shouldn't say majority, because majority is really in the track substructure, right? Because both the blue and the red ones here in the pie chart relate to really substructure related to subgrade issues, but probably the biggest component in this pie, biggest amount, 39.7% goes to really the ballast renewal and all the money spent on ballast for maintenance. Think about those, subgrade and ballast. That's much larger than even just the rail, which is one of the most expensive components, right? Even the rail. So this very much relates to what I did back in 2005 when I started a lot of my railroad research work related to track substructure. Again, as part of the AAR's technology scanning program, I started with understanding the problems of railroad industry in the U.S. We have basically in U.S. 4 major railroad companies like Class 1 railroads, and then there are 2 more of those in Canada, but those are all called North American Class 1 railroads. When I asked what their substructure problems were typically, how would they rate as most common, right? The companies listed on the top, they came up with some subgrade issues being important, like this is number 1 as the highest priority, and then drainage problems related to subgrade. But then if you look at this, in this row here where it says ballast problems, 2 companies highlighted as number 1 and 3 companies highlighted for priority as number 2. So ballast indeed sits here as one of the most important, just like you saw in that pie chart. This was quite interesting because there's very good correlation. Just to continue on Colin Basie's report from 2016, you can see that he basically listed those as soft subgrade issues and ballast degradation issues. And related to ballast degradation, how it can be maximized ballast life and improve the poor drainage conditions and things. So actually things really come together, very relevant. And indeed, because my second question in the 2005 survey to railroad companies was that out of many of the different sites, observed site problems, if there is a result of ballast, what kind of issues that you saw that you could attribute directly to ballast, right? And what they pointed out at that time was the poor drainage, very common thing that every railroader will recognize, the mud spots and the ponding and pumping and all those issues, right? And then there's alignment deviations. Again, very relevant that poor drainage associated with fouled ballast, degraded ballast as well. What that means is, okay, when ballast is new, these are just large rocks, single size rocks, typically 50 to 75 millimeter size rocks, right? But as more trains pass on that railroad track, due to attrition, due to actually contact, point to point, basically stone and stone contact, you get chipping and breaking and dusting. All of that, even if it's not coming from the subgrade, it's the ballast particle itself get churned and gets broken down, basically. And that's how you end up with typically fouled ballast. These are some calibration balls because we do a lot of imaging related work in this recognition of this degradation and quantification, actually, by doing some segmentation recently. That's the reason. But typically how we quantify that is using sieve analysis. You take a sample from the field, take it in the lab, run your sieve shaking, come up with gradation. And according to Professor Selig, and as reported in his book in 1994 with Waters, you can clearly see fouling index is the summation of passing the number 4 and number 200 sieve sizes. So usually starts from 0. 0 is clean, or 1 or 0, right? Clean new ballast goes up to 40. Similar thing is the second index that he defined, which is just percentage of material below the 9.5 millimeter size, or 3/8, we call it as inches. And that's also a similar scale, 2 to 34, you see. So that's how in practice companies really evaluate the ballast condition, whether or not it is highly fouled, heavily fouled, to be replaced or not. Well, if you don't replace or do some maintenance when ballast gets degraded like this, these are some end results. This is what can happen, right? You can clearly see the ponding, the poor drainage, all the water accumulation, and pumping with all the mud that's surrounding all the tides that you see, or sleepers. Now, the question is, can geosynthetics improve this load bearing and stability for us? Or can geosynthetics also help us to minimize these maintenance cycles of, typically the first maintenance they do is to open up the drainage channels on the shoulder. Shoulder ballast cleaners are used. That's exactly one of those in action that you see on the left side photo. And the right side photo is very heavily fouled ballast now, and they're completely replacing the whole ballast by lifting the track and basically the ties all together and undercutting basically and putting new clean ballast, right? But can we actually extend these maintenance cycles by maybe eliminating a lot of movement and degradation taking place in ballast with the help of geosynthetics? My answer to you, yes, we can do that, and that's where we come into the second place where we can use geosynthetics in the railroad track structure, which is right in the ballast instead of underneath the sub ballast. That was the soft subgrade remediation option or stabilization. Here, the second one I'm talking to you about is just basically immobilizing ballast particles and minimizing their degradation and breakage and degradation by actually placing a geogrid, especially very effective, right? Geogrids holding these rocks in place. That application requires to put a geogrid below the ballast layer right here, you see. So that geosynthetic is often a grid, which we will talk about. The grids just like, they look just like this, right? Typically, we have all kinds of different aperture sizes and shapes these days. Sizes and shapes have to be picked, matched with the typical rock gradation sizes and shapes. And typically, you just lift the trackage, and underneath that, you just place your geosynthetic geogrid more effectively. But make sure that, again, those rocks will match with some of the aperture sizes. These are some photos from Europe applications, actually, in Europe. We have more that I will show you coming up. But before I show you some really great examples of how this works, let's identify the right mechanism. And this is now agreed upon among all researchers in this field, that the identified mechanism in these aggregates, unbound aggregate layers, including ballast, lateral restraint is the way to stabilize them. That is, immobilizing individual particles moving laterally under the vertically applied wheel loading, right? That will really minimize the abrasion and the breakage of these rocks and therefore extend their service lives. With that, it's not just more immobilizing, helping the cause of minimizing degradation, but also, when you place a geogrid, for example, towards the bottom of that ballast layer, right? Make sure that you place actually geogrid below the reach of the tines. Tines are temping tines, right? Often ballast is temped with those to put into some geometry correction, the track. You want to really put them far away from the reach of tines and actually towards the bottom where there's the most movement observed is the best for capturing those rocks from lateral movement or minimizing their lateral displacements. By doing that, actually, we form a shear layer, which is stiffening the layer underneath. That helps to improve also bearing capacity too, and that helps really extending the life of ballast. So we call that stiffening because it's observed, and I will show you we're measuring now stiffness increases realized by geogrid stabilization, mechanical stabilization as well. So decreasing the time-dependent settlement will actually help us with providing an increased modulus of ballast at the time of construction, but at the same time, that increased modulus will be kept, that stiffness will be kept to carry load better, right, by minimizing degradation potential of the ballast. Therefore, the decrease of modulus in time with the ballast getting older will be minimized if you have a geogrid stabilizing the ballast layer. So that extends, again, the ballast life and reduce maintenance cycles. So it's a very sustainable application. How to match the openings of or the apertures of these geogrids with the rock sizes, right? Ballast sizes. So this is the holy grail, and there's been a lot of research going on this. My personal research favorite and interest over the years. And I'd like to show you this picture because it's from a colleague, Professor Mulabdic from Croatia. I came across with him and met with him in several of these European geogrid expert panel meetings. This is his picture, but I think it captures everything. In addition to a shear friction, with actually capturing rocks in those apertures, you're providing a very well interlocked system, completely immobilizes rocks, and that interlocked system, geogrid and aggregate interlock, is actually maximizing right there both the stiffness and actually maximizes its impact and effect. So what's the right size of the aperture to D50 average size of, median size of the material, right? According to Professor Mulabdic, that's about 2 to 3 times S over D50 in this case. But you will see that this changes whether you have a dense graded material like an unbound aggregate base course, or most often for ballast layers, these are one size. Now I'll bring to you actually the findings of others. What we're trying to do once again is directly below where the load is applied in the railroad track, you want to minimize this lateral movement of the ballast rocks, and by providing a geogrid like that, you can actually capture and you can actually make them, not move laterally, right? That naturally makes that close to the geogrid location a much higher increased stiffness layer that we call is the effect, mechanical stabilization effect. And that effect is getting less and less as you go away from where the geogrid is placed, right? That's the mechanically stabilized unbound aggregate layer concept, which applies to ballast in this case as well. It helps to provide uniform support, control permanent formation in the long term, and certainly works with the mechanism of the lateral restraint. Now, early work on this in trying to understand what aggregate size would match with actually geogrid apertures, right? Some of the early work goes back to Nottingham University in UK, 2006 tests, original tests that Professor Steve Brown started with, and either a single actuator or a series of actuators like that representing typical load coming down from individual sleepers or cross ties, and how to minimize under repeated loading, simulating a train passage, right? And the wheels and the bogies of the train. So many cycles of those, how actually you can minimize the settlement and deformation in a test setup like this by the use of Geogrids. And indeed, if you look at the picture that they have obtained, for a certain target settlement, because if you have too much settlement, that's going to end the life of that layer for you, track structure for you, right? So maybe you're targeting a certain threshold settlement value. In that case, you can clearly see without Geogrid as control and with Geogrid, there's a huge number of load cycles additional that you can do with Geogrid, right? This is something often we refer to as traffic benefit ratio. So much more traffic you can put on now for the same amount of settlement. Another way to look at it can be, this is an example, a typical design chart from the network rail in UK. Again, typical existing lines. This gives you, depending on under a sleeper, what's the support stiffness, dynamic sleeper support stiffness K, right? Depending on that value, these are the different values. A higher value is required for a higher speed train, right? Very little tolerance. But let's say the green one is the typical main line. You can actually reduce the thickness of the total track bed by using a Geogrid as opposed to no Geogrid, the green line, right? You can clearly see that you can also benefit by actually reducing the thickness of the granular layer by the placement or inclusion of a Geogrid. So that's another way to take advantage and the benefit, or realize the benefit of this. Indeed, and this is another example from UK, the main western coastline here in this case. And this is from Phil Sharp, now with ACOM. Very nice application here. Everything was changed except for the rails, new ballast, new sleeper, and using Geogrids now at the bottom of the ballast layer for ballast stabilization case. They were able to actually really cure, or I would say, really fix the issue of a recurring settlement every other year or every 2 to 3 years. This is exactly that curve that shows you a typical accumulation rate of 1.43 millimeter per year, right? And in a matter of few years now, you're accumulating more settlement. By actually adding the Geogrid in this timeline here, they were able to get a much lower rate of accumulation of deformation. So that tells you that the recurring problem over the years, they solved by the use of Geogrid very effectively. Another very effective example, this is one of the very few that you will find actually in bridge approaches as a transition zone, we call it often in traffic applications, right? Whether highway or railroad. This is the bump at the end of the bridge issue, very common issue. Sometimes an approach slab, like a tapered concrete slab, as they denote here, a show, is something people like to try, but often that doesn't solve the problem. That just extends the location of the bump. The bump now also moves ahead and still at the end of that rigid extension. So, but to smoothing that transition is something they've done very effectively here by many layers of Geogrid placement. These dashed lines are several layers of Geogrid. They were able to really get that zone, that's the transition zone, go from a very smooth pile slab into that transition zone, and the bump didn't come back. So basically they got rid of the bump at the end of the bridge issue by smoothly transitioning with Geogrids. Very interesting. Finally, this is one of the most interesting of all. This is a study that was supported by, I think, the National Science Foundation, EPSCoR, I believe it's called, in UK, with Professor Steve Brown. This is very interesting because Professor Brown, in this case, went to a geosynthetic geogrid manufacturer and asked them to actually come up with different aperture size grids manufactured for typically the constant size of ballast often used. In this case, it's a typical 50 millimeter size of ballast, as you see new ballast in this test setup. And different size, different basically square aperture grids were manufactured just to see which size will fit with the most typical ballast used in most of ballast to track lines in the UK, right? And they were looking at under the actuator then the settlement demands in time with many load cycles and applications. And if you consider now the settlement is accumulating with number of load cycles, they even went ahead to use a steel grid, but also the polymeric geogrids, right, with square apertures. And the 65 number stands for 65 millimeter for the square opening, but they tried 32, 38, 50. And right at the 30,000 cycles, the settlement demand is what is shown in this right-hand side plot. And you can see that actually minimizing the settlement at that 30,000 cycle was achieved with the 65 millimeter aperture opening. So 65 millimeter aperture to 50 millimeter size of the ballast. So there is a 1.3 ratio, right? That was very interesting to find. And eventually we did discrete element modeling of this experiment. We got the same thing. I will show you that later on in our research. One other interesting aspect, I became part of this as well, and I went to Hungary to the university where they used a multi-level shear box test. An interesting concept again, which is and a very relevant thing too. Wherever you place a geogrid in a ballast layer at different levels above, basically you do a shear box horizontal shearing to understand at what level, that's why it's multi-level, right? At what level the force will be maximized, and how this effect of the geogrid can be seen with or without geogrid in a shear box experiment. This is a quite large setup actually in box, typically very good. That means you have no end effects and it's kind of realistic, and these are results. If geogrid is here at this level where the x-axis is in this plot, right, where's going to be the shearing plane? Exactly here, or just a little above, about 10 centimeters above, about 20 centimeters above. So these are the data points that actually were obtained for force values to plot these charts. In a compacted ballast layer, you always have a peak like that, whereas the other non-compacted loose ballast, and always the red line in this case you see in both cases, compacted and uncompacted. Red case is with geogrid. The one with the blue color is no geogrid. So you can clearly see the improvement in the shear taking ability of the material above the geogrid much higher. Now, how did geogrid come into US practice in the use? Some of my colleagues and one of my students actually who was working on this quite hard with the American Railway and Railway Engineering and Maintenance Association, Maintenance of Way Association, ARIMA. They were finally able to get ARIMA in 2008 to accept to use geosynthetics, and especially providing geogrid for stabilizing ballast and sub ballast layers. And the picture that you see here is one of our professors at the University of Illinois at Urbana-Champaign from 1920s. The time of the railroad boom, when Professor Arthur Talbot came up with all the aggregate gradations. He did pioneering work in concrete and aggregate optimum gradations, as well as like dense graded, right, as well as railroad at that time. The thickness design of the ballast comes from basically his work that we always use. That's how we determine some of the thicknesses, minimum 12 inches or so we need below a concrete sleeper or tie usually. Things like those come from basically protecting the subgrade or subballast, as well as what is the pressure at the bottom of the tie. That gives us that H thickness equation, right? But nevertheless, that picture, that slide tells you that now we have in the ARIMA spec, our railroad spec, use of geogrid. And with that, they were able to go ahead and use in some of the applications, like the Utah Light Rail project in this case, by putting a geogrid below a sub ballast, kind of the subgrade stabilization application. Remember, they were able to go from a 12-inch to 8-inch thickness in the case of sub ballast, which is quite useful to have that. And another application where they looked at the differences in triangular aperture versus rectangular aperture geogrids. In this case, in Wilsonville, Alabama, these were staging tracks, 10 inches of ballast and about 8 inches of sub ballast underneath. The experiment had considerations for instrumenting actually railroad track to understand how deformations take place from just visual observations, just like looking at some of those points on top of the ties, as well as they placed pressure cells at the bottom to understand subgrade pressures, what subgrade pressures were measured, right? Here is your total station, and that's how they're observing the top of rail or top of tie displacements. But from the pressure cells, what they observed, very interestingly, what pressure levels go on top of the subgrade. And in the case of biaxial or triaxial or, again, rectangular or triangular aperture grids, how different they perform. And triangular happen to have actually a little better bridging effect and stiffer maybe layer to cut down the pressure even further, right? That's a good thing to see. One other aspect is also another experiment research project tried with a smart rock concept that was developed by one of my PhD students. Now, a professor at Penn State, Professor Hai Huang, developed this smart rock idea. The outside shell is basically 3D printed, and inside there's a multitude of sensors, basically from all triaxial, three-dimensional accelerometers, gyroscopes, as well as pressure and temperature sensors, right? So when you place this in a setup like that and you're doing cyclic loading, actuator loading tests, and now without geogrid and with geogrid, you want to observe the movements of this rock, which all has the instruments near a geogrid, or in the no geogrid case, they were able to see the typical particle accelerations in 3 directions, right? X, Y, Z directions. And with geogrid, the same location, see how particle accelerations and vibrations minimized. What's really interesting is that actually particle rotations were recorded much higher in the without geogrid case, and they drastically were decreased to nothing, no rotation at all in the case of with geogrid. So this kind of a smart sensing technology can help us really detect and show clearly the effects of immobilizing and holding rocks in place by the geogrid, which is effectively what it does. Another field application from TTCI, Association of American Railroads. I was somewhat involved with this field project. Again, some of my colleagues got to work. A recurring problem of wet embankment condition for a railroad track. This is Norfolk Southern side in Ohio. And for about 4 or 5 years, they were able to place a geogrid like that and cut down the recurring settlement issues. Then I think in 2017 and 18, when they finally visited the site, they realized there was some embankment movement, like deeper ground movement in this case. But until that point, really, ballast stabilization worked with geogrids very effectively. So I will only show a few other slides from my experiments and research at the University of Illinois, because we were intimately involved in actually doing a lot of field work and discrete element modeling that for 20 years now I've been working on this with the ballast settlement and unbound aggregate movements and relating those to realistic way of capturing particle shape, angularity, and typical sizes and shapes, realistically creating then individual particles with the typical crushed stone shapes and texture and angularity and everything. That's something we have been doing a lot in research at the University of Illinois, and relating those to actual problems of ballast fouling and modeling of the ballast layer and discrete element modeling, as well as settlement right here as the bump at the end of the bridge, right? right here, the transition zone differential settlement issue. So some of these things we have been studying all along. And having said discrete element modeling with the individual particles in contact, this is very much particulate medium. You cannot assume continuum. So you have to go back to a discrete element methodology where contact forces have to be analyzed in a kind of an iterative time iteration-based domain where actually equilibrium equations for, again, angular as well as static equilibrium conditions are satisfied with time iterations. So that's the basis of discrete element modeling. I will show you some results of that in our analysis. Actually, what we did discrete element modeling on was actually based on a ballast testing specimen in the lab, and this picture shows how ballast samples we tested were actually reinforced or stabilized by the use of geogrids, right? This goes back to some of the actually interesting discussions we had in the 25th year anniversary, or we call it the Jubilee Symposium of Geogrid in London, when we had a meeting in 2009, where Dr. Giroux had a very nice paper also he presented on what are the things that make this aggregate interlock, geogrid and aggregate interlock, right, to come together. So you can clearly see that, as he also stated, the factors that this interlock depends on are aggregates, gradation, and shape properties, both size and shape, in addition to, of course, geogrid's aperture size and the stiffness of the rib and shape of the rib and the depth of the rib, depth or the width, right? But as well as the compaction conditions, you also saw that in the multi-level shear box and loading conditions. They all have to be evaluated for the proper interlock. Having said that, the second most important thing after size on aggregate particles is the shape. And my almost 30 years of effort since late 1990s to quantify shape properties such as the flatness, elongation, angularity, surface texture by quantifiable indices. And for that, we've been using image analysis technologies. This is the enhanced University of Illinois aggregate image analyzer. It's a second generation one with now color cameras and color thresholding to actually get the top, side, front views and bring them together to come up with realistic 3D polyhedrons as ballast particles in discrete element modeling, right? By capturing exact properties as indices from an actual rock placed here on a conveyor belt, right, in the view of 3 orthogonal cameras, we are able to come up with a 3D polyhedron shape and put them then into a discrete element model like that, which we call it, the one we use at the University of Illinois is blocks 3D, and we can actually come up with an actual track, ballasted track to look at settlement issues, tamping issues with tamping tines, it's consolidation, it's actually lateral stability, all kinds of things we've been studying. So we use that technology to do the modeling, discrete element modeling of a geogrid ballast stabilization study of Professor Brown's from 2007. And if you remember, this is the curve that we saw in the actual experiment, how the different aperture size of the aperture size of 65 millimeter square aperture grid actually matched with the 50 millimeter size ballast particles to minimize the displacement, right? We didn't go all the way to 30,000. It's a very time-consuming simulation, but even at the 40 cycles that we could do in this case, at similar void ratios, we were able to capture the same and get the same result of 65 millimeters, very effective, right? These are the kind of things really come together very nicely. The next thing we did was then a large ballast triaxial test, right? This is 30 centimeter in diameter by 60 centimeter high specimens that allow us to go to 2 to 3 inch top size, 75 millimeter top size rocks placed in this. Typically, you have aggregate top size to basically actually diameter about 5 to 6 ratio, and that's exactly what you can build a ballast specimen here. in this kind of a triaxial test. We can do 3 different LVDTs, 120 degrees apart for the axial deformation. And then in the middle, we have a circumferential extensometer just to get the bulging also measured from typical tests. And that's what we've been using to actually place geogrids in some geogrid stabilized ballast specimens to understand how ballast works in typical triaxial tests, right? And this is the aluminum mold, that's the split mold, that's how we build in typically 4 layers, compact each layer, and in the middle you place, for example, like you see in these pictures, either a triangular aperture grid or a rectangular aperture grid, right? And we run shear strength test and permanent deformation test. So here is an example of an actual shear strength test, which is a rapid shear, we call it, really very fast, 5% deformation strain rate per second. And you can see the huge bulging and things. So actually, we were able to simulate this using the discrete element method, and I'll show you the simulation of that as well. But one thing we always, worked around with the actual experiment was that where should we place a geogrid in the specimen for maximizing shear strength or minimizing permanent deformation? So certainly middle is where the bulging is taking place, but what if we put 2 geogrids? Would that be more effective? And where would we put the geogrids? What location, what height in the specimen, right? So eventually we found out what makes sense is that where the bulging is happening in the middle, putting 2 geogrids close to each other, like 250 millimeter from the top, 250 from the bottom, see, that gives you the highest shear strength. That was the case for a rectangular aperture grid, and that was the case for a triangular aperture grid. The triangular aperture looked similar with 1 versus 2, actually, but anyways, still, that worked out very well as well. Well, the concept is you want to capture where the bulging is. The lateral movement of the rocks and geogrids nicely hold that, prevent the bulging. So here are the discrete element models created to actually model this, the experiment. And this is a triangular aperture grid in the middle, and then there is a rectangular aperture grid in the middle. And interestingly, the outside, where you see those overlapping elements, those are the flexible, those are representing flexible membranes. We just allow those to overlap, those blocks, because they have to allow the bulging of the specimen too, and they're not rigid. They can overlap, but only the outside cell membrane elements as blocks can do that to allow for the bulging. And indeed, that bulging happens as the specimen is going through that. Oops, you see in the middle, they're moving out, allowing the bulging to happen. That's how we simulated that experiment. And you can see what happens in a shear strength test here, how the specimen deforms with 5% strain and 10% strain, the shortening of the length. We could actually model the same thing, as you can see. All right, and when we looked at out of those 8 different locations of the membrane elements outside the specimen, which ones are moving out the most? And that's what this is showing, right? The ML5 happens to be like in the middle. Again, it shows us clearly the bulging happening in the middle in the experiment as well. So in short, in summary, again, you see the highest shear strength is achieved with 2 geogrids very closely placed right in the middle where the bulging is. If they're far away from each other, they don't do any good, right? They may even create some slip failure plane, because in the middle part, you have the shearing effect of the specimen realized, and that really doesn't do any good. You need to bring them in the middle where the bulging is prevented. Same thing for cutting. Permanent deformation and shear strength are very much similar. The only difference is in permanent deformation testing, now you have cycles to go through, right? and the rest periods in between, just like typical wheel loads repeatedly are applied. And when you realize that with so many load applications, now we're looking at how much deformation, permanent deformation, is accumulating in a stabilized specimen in the middle, for example, here, with either rectangular or triangular aperture grids. And you can clearly see that permanent deformation is cut down. This is an actual test result, by the way. We also simulated it too. But the test result gave the same thing. And the one is test result. I think data is they're matching each other. We had both published in 2018, actually. Yeah. So that was quite good. In conclusion, from field lab and DEM discrete element modeling studies, clearly we showed that geogrids stiffen and hold the aggregate layer through the interlocking. So in order to understand the interlocking and what factors play a role, we use the imaging-based techniques to exactly simulate and characterize the aggregate size and shape. And therefore, that's how we studied that stiffened zone. And that really helped us to understand the micromechanical interactions between geogrids and aggregates. Yet, there are still questions to ponder, which is, I know I showed you a couple of different experiments. What's the aperture size, the appropriate geogrid aperture size, and the gradations? And there's still somewhat differences in researchers' results. And things like, Brown came up maybe with some general range, Professor Steve Brown. Glenn McDowell did some more work, came up with some other 1.4 ratio versus 1.2, 1.3. Some others relate back with D50 instead of maximum top size of the specimen, right? So there's still differences in what's the right match. But it's not just the size match. There's also particle shape match and everything, plus the geogrid properties, and even the depth of the rip, for example, and the junction. All of those things play a role in this interlock, right? So from that perspective, the end effect of this lateral restraint mechanism is that you're creating a stiffened zone above the geogrid, right? That stiffened zone is helping to minimize the permanent deformation in time because it's stiffer and it stays stiff like that. And it doesn't allow, again, aggregates to go around to create a mechanically stabilized ballast layer. So what if we could come up with a way to measure stiffness? Measuring stiffness is so difficult, right? But are there techniques that we could try? And this is the last part of, only I have a few slides left here to finish. Last part of my presentation, which is really interesting because, again, for about 20 years, I've been questioning how can we understand the stiffening effect? And, a postdoc who started working with me and we started looking at ways to be able to use the shear wave transmission, shear wave generation idea to understand local stiffness quantification. And this is a TRB paper as a result of that, using the Bender element shear wave transducers. What Bender elements do actually, these are piezoelectric sheets. And when you have a mounting base like that and you place this mounting base right outside of a specimen, basically through the membrane into the specimen transversely, you just place them. There is a source or transmitter, and then there's a receiver. And with the distance in between, now you're generating a shear wave. As the shear wave travels, a certain distance is picked up by the receiver, and by dividing the by actually knowing the time that it took, distance divided by time, you get a shear wave velocity, right? So this piezoelectric sheet right here is doing the fishtail, right? Here it shows us up and down. That's creating a coupling with the medium. That's creating actually the shear wave, and that shear wave transmission helps us to calculate the shear wave velocity, which is linked to a small strain modules. There's an equation to calculate this. So that's exactly what we did. To capture the mechanically stabilized zone above a geogrid installed in the middle of a specimen, right? So we had 3 pairs of source receiver sets, basically placed like that. And all you need to do is a signal generator for these sensors, and then pre-post amplifiers with an oscilloscope where you actually control the signal shape. That's how we made this part of our typical resilient modulus test equipment. Interestingly, on a specimen like this, when you measure the resilient modulus from the full length of the specimen or height of the specimen, right? Stabilized or not stabilized, these are stabilized with square or triangular aperture grids, or unstabilized. For different stress states, these are 15 stress states we usually go through, right, in a typical resilient modulus test, you can clearly see that there's not much difference, really, and you cannot tell because some of the effect of more immobilizing the aggregate by the grid is kind of a local phenomenon. But resilient modulus requires obtaining strain, recoverable strain from the full length, height of the specimen. So it really doesn't capture the effect of the geogrid. Whereas with the Bender element shear wave generation above a geogrid like that in the middle of the specimen, very interestingly, we were able to get the local stiffening effect quantified. So near the geogrid, you can clearly see that that's the red triangular symbols that says middle of the specimen right here, above the geogrid directly. Much higher shear moduli at the same stress states, 15 stress states captured, compared to the top being the, on the top, the pair here shown, which is far away from the geogrid, that's much lower. And the one in between is in the middle, right there. So you can clearly see the mechanically stabilized zone, the concept captured by these horizontally instrumented Bender element sensors pairs. And with that, we did run through square grids and triangular grids and different types of grids that also showed us such effect. And we were able to capture, but interestingly, in a no geogrid case, from those 3 different locations, 3 different pairs, they didn't come up with any difference, right? Because there's no geogrid to hold the material, and lateral restraint, mechanism is not applied in the case of no geogrid. That was great. A full application of this to 15 stress states with triangular grid and square grid, you can clearly see a shear modulus ratio that we obtain as we go closer to the grid. Grid is right on the x-axis location, if you think about that, triangular grid and a rectangular grid. So this is something I presented actually in Atlanta in a conference, but this is how we capture that mechanically stabilized zone, right? And again, just a simplified version. If the grid is here in the middle of the specimen or at the bottom of the layer, as we do in the field, right? If we place some of these sensors, we can capture the shear wave from shear wave measurements, the small strain modulus properties. And that's exactly what we are doing in this case, placing on a geogrid over a geogrid that is basically digging down in a constructed aggregate layer. This is more of a payment base course layer in this case. Just to show you, we built with some funding from the Army Corps of Engineers who invested in this technology, sensor technology now. We have actually come up with a frame where we have protected source and receiver sets all in plane, supposed to actually do about 4 feet, 120 centimeters apart. That's how we're transmitting in this medium, just directly above the grid. As you see, it's above the grid. And we've also placed this kind of a Bender element field sensor in other locations, actually 3 locations in the FAA's test center, test sections here. The one immediately above the geogrid, upon construction, gave us the higher shear wave velocity and higher shear modulus, as opposed to 4 inches above, and as opposed to in the south section, there was a control without the geogrid placement. So clearly we were able to quantify all this. Last 2 slides, just to show you the most recent focus, what we are doing in the lab right now, actually, as we speak, we have a box where we use that as for calibration, and one side is usually have a plexiglass we can see through. This is a box that can actually take a ballast or different aggregate particles like that. And we have a smaller size Bender element sensor with a source and receiver that's about only 30 centimeters apart. These are with the large rocks. We are coupling the, again, Bender elements, and we are able to send a shear wave transmission like that, and obtaining some values right from that, as well as a French Panda penetrometer we've been using also from the Panda to back calculate some of the shear wave velocities according to the stiffness of the medium we penetrate with the penetrometer, right? And from that, now at different fouling conditions of ballast, we are able to develop a shear wave velocity profile both from the Bender elements and the Panda, which helps us actually to compare the values and validate some of our Bender element values with the Panda equations as well. And with that, we can probably come up with a better way of quantifying the ballast layer stiffness increase over a geogrid in the field as well. I know I've taken probably around 70 minutes here instead of 60 minutes, but really I'm at the end, and this is my last slide here. Thank you very much for your attention. So I'll be happy to take questions. Thanks.
Oh, Errol, thank you for that incredible presentation. I think for the whole audience listening today, they can detect the passion you have for this topic. It comes through. Actually, it's interesting. I'll make one other slightly personal comment about this, is that the research into the combination of geogrids and ballast goes back more than 35 years. In fact, some of the very early work was done by one of our earlier speakers from last year, Richard Bathurst. He did some testing published about 1986, which was very much what we call empirical approach. But now I think what we see with the work you're doing is you're trying to really get inside there, trying to get inside and to understand far better what's really happening. And things like the Bender element work and I mean, this very clever smart rock.
Right.
When I first saw smart rock, I thought, wow, that's really smart, because it's actually telling you what's going on inside the ballast or the aggregate layer. And I thought that was a relatively inexpensive but very clever piece of work to understand the fundamentals of what's going on. So, and Errol, you illustrated so many great things there. We have quite a lot of questions, so I mustn't hold up too much. Some of them are quite short and some of them are quite long. So I'll take them from the top because that's the order they've come in. So we have from, if you can see them as well, but from Zoe Lynn, are there any software or design guideline for ballast stabilization?
Not that I'm familiar with. I know there are some software programs available in general for geogrid stabilization. One that I'm familiar with, again, is more for payments, I believe, payment-based courses and sub-bases, but not for ballast, as I understand, as I remember. So,
yeah, I think I agree. I think I agree, Errol. I think there is something for sub ballast, but not necessarily for ballast.
I mean, I can relate to only one company who has a good version, good software for payment based, but not for railroad ballast. Yeah, right.
Okay, no, great, no, thanks. So the second question from Raihan Aditya: what standards are used for geogrids to improve subgrade stabilization? So other standards that relate to the geogrid use.
What standards are used using geogrids to improve subgrade stabilization? Well, subgrade stabilization application usually lends itself to soft subgrade conditions, and more commonly, I think in the case of payments, it's more construction platforms and things, and CBR, California bearing ratio numbers, again, strength parameter, right? Something below 3 or 4 at the most. And whenever you go into 3 to 8 kind of CBR, that's more like you have to have a complete pavement. Or again, for railroad, I don't think this is very, very commonly stated, or we have clear guidelines on that either. So, yeah.
Okay, no, thanks, Errol. Actually, I forgot to mention to everybody that, of course, Errol is speaking to us, I assume, from his home, which means that he's exactly a 12-hour time difference from us. So he's keeping going incredibly well. If you look at the time here now, 11:30, that means 11:30 with Errol as well, but the other 11:30.
I hope I don't look very sleepy. So
No, you definitely don't. Okay, we have a long but very interesting question, CK Lee. It is understood that the geogrids work by providing lateral restraint. However, I suppose we should also consider the strain compatibility of the ballast and the geogrids. I suppose that the lateral stiffness of the ballast and the geogrids are magnitudes apart, i.e. the ballast would have to displace significantly before the mechanism of lateral restraint becomes effective. How then can we conclude that geogrids are effective in a statistically significant sense in providing significant lateral restraint? I understand that much research work has been done to prove its effectiveness. The mechanism based on conventional engineering sense seems off, unless the lateral restraint stiffness offered by geogrids are larger and not similar in magnitude to compared to the ballast. So it's a very interesting, long question, but I think a lot of what you've been talking about is tucked away inside the answer as well.
Right. What I generally talked about and showed in the work, geogrid work that I did, the type of geogrid typically, mostly I used was stiff geogrids. These are either extruded geogrids or punched and drawn geogrids. Unitized kind of, right, from punching and drawing and right. So from that perspective, these are stiff grids I used, and there's not much of really flexing of the geogrid. But there are other types of welded geogrids. There are other types of geogrids that will come in different mechanisms for capturing the rocks. And this is something actively, we have a study started with our Illinois Department of Transportation here, and we're looking at different types of geogrids, exactly with the Bender element sensor now, understanding, quantifying stiffness increases and things, and that's an actual study we have initiated and collecting different types of geogrids for evaluating those. Yeah.
No, thanks. Actually, the next question is quite closely related, but this is also from Zoe Lin. Most stiff geogrids are presented in your presentation, of course. How about the performance of flexible geogrid for ballast stabilization?
That's exactly my answer I already gave you, which is I'm not that familiar, and I haven't done much. I don't have enough experience on flexible geogrids, but that's something now we're getting more into in that comprehensive study. Yeah, I'm collecting all kinds of different types of geogrids, including those flexible geogrids. Yeah.
Okay, right. Thanks, Rob. Now, from Claudia Browning, did you perform cyclic tests in the triaxial test? If so, what frequency did you use?
Yeah, we did. Indeed, it's not a frequency when you, I mean, truly, when you call it a cyclic test, frequency is the way to define what it is. And what we call in vehicular loading, and that's how I believe it's supposed to be, is repeated load tests, we call them, which means for correctly representing the actual field stress states, even in the case of a train loading, believe me, there's rest periods in between wheel load applications, pulses. So therefore, you have to give, according to the speed of the train, according to speed of a truck, for example, you have to take into account what's the load pulse duration and what duration of rest you have to give instead of a continuous sine wave, for example, cyclic, right? So that's why it's not the frequency, but we usually talk about commonly 0.1 to 0.4 second load duration and about 0.5 to 0.6 goes with 0.4, and then 0.9 up to maybe goes with 0.1 second rest periods with them. But all of these have to be nicely adjusted according to the typical speeds, and at that depth, what speeds are felt in terms of actual load pulse and actual rest period. Right. Yeah,
it's I think it's a big topic.
I know in ballast testing, a lot of colleagues, close colleagues, actually, they just simply run cyclic tests. But in my opinion, cyclic tests give you a harsher picture, a much harsher treatment to ballast than typical vehicular loading. And what that means is that you apparently get, maybe it's conservative, much worse conditions realized through a cyclic. If you don't give any rest period to the specimen, that means you accumulate much more permanent deformation than realistic, for example. Right.
An interesting point. Yeah, so this is another from C.K. Lee. What stress path in the traxial test are you following? Conventional drain shearing? Is it conventional drain shearing?
Most of our samples are partially saturated, and that's, typically we have open valves and things, but, never we get to a saturated state. You can do that actually with some pore pressure measurement, but often that's a very bad case. We don't want to keep any of these aggregate layers saturated, so it's customary to run them with open drainage valve, and it's usually very much partially saturated anyway. Simply like that.
Okay, thanks, Harold. Okay, so from Slamat Widodo, which effective laying down geogrid at the top of the subgrade, which is more effective, at the top of the subgrade or within the sub ballast, based on your experience in increasing bearing capacity? So this is all about location of the geogrid in the layer.
Right. More commonly, I think it's the bottom of the ballast, sub-ballast, for the subgrade stabilization application. And I think this makes sense from the point of, for any kind of vehicular traffic loading and subgrade improvement that you do, you want to put the geogrid usually on top of that subgrade, especially it becomes the best. Yeah.
Okay, now C.K. Lee again. On the placement of geogrid below the ties, and this may be similar, I haven't read it yet. Is it show the geogrids the larger the lateral restraint? I said closest to the base of the tie, I assume. For the practical application of geogrids below ties, the placement of the geogrids seems to be way down below the zone where large ballast deformations are expected. How then do you justify the placement of geogrids that are far below the ties?
Actually, I'm not sure if that's the case because, well, first of all, very shallow in the ballast. If you place the geogrid, you always have an issue with maintenance cycles and the tamping times. That's where the practitioners will really hate to do that, putting shallow. But from my experience, actually, if you want to protect from excessive permanent deformation, maybe it makes sense to bring the geogrid a little higher. In a shallow depth or shallower depth, but in ballast application, again, you want to extend it down because you want to put it farther away from the tamping tines. The second thing is that usually at the bottom of the layer, if you think the layer is acting all together, that's where usually the most spreading is taking place, because the bottom of the layer is where you have horizontal tension, of course, built from a bending point of view when you think about that, and that's really where effectively you can hold the materials best. I gave you the example of in the triaxial specimen, the bulging in the middle, right? I think from the way of the layered system of the layer is where you have the spreading the most, or the tendency, and that's where it's cutting that tendency, not allowing the horizontal or lateral working. Yeah.
And I think then we'll bring this to an end, Errol, and we'll let you get some sleep. So John Buckley, John Buckley actually is my colleague, and he's listening in from Australia. So there we are. We often do have people listening in from way outside Indonesia. So regarding the aggregate image analyzer, how many separate aggregate image capture runs were required to make the DE model shown in the next slides, obviously when you were talking, meaningful and representative of actual behavior?
Yeah, actually what we do is we sample the ballast, and then ballast is usually one size, so that helps us, although even though it's one size, you still have some smaller rocks to little larger rocks, so it's not that big of a variation. Usually up to 100 rocks or so, when we individually quantify their shapes like that with 3 cameras and 3D, we get all the properties right. So we don't have to go more than that. Statistically, I think that's usually enough. Assuming that the same rock is used in the project, like the ballast aggregate, right, from the same quarry and everything, you would assume that then the particle shape properties from that representative sample, we analyze, again, one by one, but up to maybe 100 individual aggregate particles, that should capture typical average angularity index, flatness elongation, basically the largest size, the smallest size, what's the aspect ratio, right? That's the flat and elongated ratio. And all those, that's how we capture those to create the DEM models of those.
I must say, for me, when you look at the work you do for that modeling, it's just quite incredible to see how we've progressed in general, and thank you for illustrating all that. Okay, we have two questions left from the same person. In fact, this is from Pak Go Chi Leong, who actually was our speaker last month. He talked about a very different topic, about the issue of clay shales in reinforced soil structures, but he has some questions for you on today's topic as well. First one is, how is the fouling index determined?
Yeah, the fouling index is, as I mentioned, it's a simple practical definition, and in this country, in the US, that is, practitioners are very much sticking with that. I know there are different indices, like there is a different on VCI, I think it's called, by Professor Indiradna in Australia. Different indices have been developed, but this is based on just percent passing number 4 to percent passing number 200, and that simply captures what's fouling index, right? But another one called percentage of fouling is just basically percentage of material by weight below the 9.5 millimeter sieve size. So that's how they usually account for that. Yeah.
Okay, we have one last question and one last comment. So a last question from Pat Go, and this is actually a topic which I think you'll be very keen to talk about a little bit, was from your research, how high is the effect of interlocking or lateral restraint measured from the geogrid? How many centimeters height? Can it reach 80 centimeters or 100 centimeters? Errol, you'll definitely be interested to answer that question.
No, excellent point. And that's been something for many years. With my collaborations with some of the DEM researchers all around the country, all around the world, I should say, like Professor Glenn McDowell, for example, from Nottingham. He did a lot of work with Nick Tom. They did a lot of DEM work. Some of the German researchers who work with some very interesting geogrid manufacturers supported research. Itasca is the company. The PFC 3D, again, some commercial discrete element modeling software. Many of them come up with typically 4 inches. Well, I should say 10 centimeters or so is where that stiffened zone is. Okay, but in our experiments, very interesting things we find now, especially with the Bender element sensor, depends on the compaction. That can be extended, the effect of the geogrid, well compacted versus loosely compacted sometimes, and how that interlock happens with the different gradation and particle crushed versus uncrushed particles, for example. We are seeing there are differences in those influence zones, stiffened zones. So that's the effect of how good your aggregate interlock is and how well compacted, right? They all have an influence on that mechanically stabilized layer concept and the effect of the geogrid, how far that extends, basically. But 100 centimeters, 80 centimeters, those are too high. That 100 centimeters is a meter. So we're talking about 10 to 20 centimeters at the most. Yeah. So
It's a good topic, and I think there's no one answer to that question. But no, thanks, sir. Okay, well, we have number 12. Number 12 is actually what I'd like to say myself from my colleague John Buckley again. He says, thanks for a very interesting presentation, Errol, which is exactly what I'd like to say as well, and taking time to answer my questions and many others. And he says, good evening from Australia. And Errol, I'm going to say myself, good evening from Indonesia, for you anyhow.
Good morning to you all. I guess Australia, maybe afternoon already.
No, that was a really excellent presentation. You put a lot of really up-to-date information in front of us, and people will look forward to reviewing what from the PDF of your slides, I'm quite sure. So it's just my job now to bring this part of our webinar to an end and to thank you again. Just to let you know that you're welcome to go off to bed, or if you'd like to hang on, it's just a few minutes for the quiz. You'll be told how to get in there either through your computer or for your mobile phone. We're using what's called menti.com. So what I'm going to do now is to hand back to, actually, does number 13 come in? Pago, in relation to that question, is it applied to MSc walls, or is it only to the? So I think this is the extent of the effect of a geogrid. Is it applied to MSc walls, or only to the kind of the ballast or road concept? Aggregate
interlock with geogrid is a concept for any kind of aggregate layer this is the way it's supposed to work, right? In general, of course, in the case of typical pavement or railroad track applications, the load is coming always, and repeatedly applied from the vertical. The scenario is different than an MSc wall. Now there is horizontal reinforcement, right, and all that. And sometimes the biaxial nature of, or omniaxial, whatever you call it now, with hexagonal or triangular, whatever apertures, arresting the movement of particle in all directions, maybe just linked to one direction only in MSc wall, right? The uniaxial kind of grids versus, right? So, but I think from that point of the interlock and capturing and immobilizing the rock for any unbound aggregate layer, I think that's what Geogrid is doing. So
I think that's a very good last word. Errol, I will not ask you to answer any more questions. There aren't any more. That was a fantastic job you did for us. And one more time, thank you very, very much. And I shall hand back to...
Thanks for having me. Yeah.
Oh, it was a great pleasure. I'll hand back to our MC, Rifa, to take us through the rest of the event today. Errol, thanks again.
Great.
Okay, once again, thank you, Errol Tutumluwe, for your excellent presentation, and thank you also to Bapak Mike Dobi for guiding the session. Next, I would like to invite all of you for the chance to get the very interesting prize by joining a very short game we have prepared. The first winner will get 150,000, and the second winner will get one. Disclaimer before we play, but for technical reasons, only those who live inside Indonesia are eligible to get the prize. So you cannot go directly to your browser on your phone or your PC and type menti.com, menti.com, menti.com. You have to type the code number shown on your screen right now, or also there in the chat box. The code is 7289. 5837. Once again, the code is 72895837. Go to menti.com and put the code 72895837. Then fill in your name and make sure that it is the name you submit in the registration for this webinar. So later, if you win, the committee will easily contact you for the prize. Remember, the prize is very interesting. For two winners, we have 150,000 rupiah, and for the second winner, we have 100,000 rupiah. You will not want to miss this chance. So for those who live inside Indonesia, and also everyone who wants to play this game, go to menti.com, put the code 72895837, and fill in your name. Okay, let's see how many people have joined us. Okay, I'm gonna share it to you. So we have 25 people. I will be waiting for more. Go to menti.com and then fill in the code 72895837. I'll be waiting for another minute. So do we have the total of 250,000 rupiah will be given to two winners. The first winner will get 150,000 and the second winner will get 100,000 rupiah. But those who live inside Indonesia are the only one who eligible to get the prize, but everyone can join. So we have 32 people playing with us. 8, 7, 6, 5, 4, 3, 2, 1. We're going to play for the so all the questions are prepared by our speakers, Errol Tutumluwer, just for your information. Okay, let's go to the first question. Answer fast to get more points. Let's see. Which of the following listed below is not a function of railroad ballast layer? Sorry for that. The first option, is it provide drainage? Is it to reduce stress to underlying layers? Third option, provide void storage and resiliency? Or is it to prevent subgrade attrition? So which of the following listed below is not a function of railroad ballast layer? Is it the first option? Is it the second option? Is it the third option? Or is it the fourth option? You have roughly 10 seconds to answer, but if you answer faster, you will get more points. 5, 4, 3, 2, 1. Time's up. Let's see what is the correct answer. The correct answer is the fourth option, to prevent subgrade attrition. Let's see who lead the leaderboard for the first question. So for the first question, we have Dio Alif Utama, who is the fastest, but we still have 2 more questions, so brace yourself. Now, let's go to the second question. Answer fast to get more points. Which of the following listed below is not a benefit of geogrid mechanical stabilization of ballast? Is it to provide an increased modulus of ballast at the time of construction? Is it the second option, mobilize tension membrane forces in geogrid to improve load carrying? Or the third option, minimize degradation of the modulus of ballast over time? Or is it the last option, extend ballast life, for example, reduce maintenance cycles? So is it the first, is it the second, is it the third, or is it the fourth option? Which of the following listed below is not a benefit of geogrid mechanical stabilization of ballast? You have 5, 4, 3, 2, 1. Time's up. So the correct answer is the second option, mobilize tension membrane forces in geogrid to improve load carrying. Okay, let's see who leads for the second question. Oh, I think it's different now, the leader. For the second question, Zulfi Triansyah Putra leads the leaderboard, but let's see. For the last question, you still have chances to get the total of 250,000 rupiah. Okay, last question. You can answer fast to get more points. According to Dr. J.P. Giroud, which of the following is not a factor to influence level of stiffening due to geogrid aggregate interlock? Is it aggregate gradation, which is size and shape, form, angularity, and texture properties? Is it the second option, geogrid type and aperture size? Or is it the third option, ultimate tensile strength of geogrid? Or is it the fourth option, field compaction effort? You still have time, but you still have the chance to get the total of 250,000 rupiah. So according to Dr. J.P. Giroud, which of the following is not a factor to influence level of stiffening due to geogrid aggregate interlock? 3, 2, 1, time's up. Let's see. The correct answer is the third option, ultimate tensile strength of geogrid. Let's see we will have two winners for today. The first one and also the second one with the most points. So let's see who will win the quiz. All right, congratulations for the first winner is Zulfitrian Syahputra with 2,000.